But I'll repeat myself. I was talking about the refraction of light. And I was asking Eric, I was saying that the longer the wavelength, like in the visible spectrum, the red is a longer wavelength than the violet. And so the red is going to refract the least out of all the colors. It's going to be at like 750 nanometers versus the violet, which will be about 380. And then I was looking up, and I was looking into marine radar, boat radar, and I made a video about this before. But the standard explanation of boat radars, they will tell you that the longer wavelength bends more because they're believing that they're living on the convex surface of the Earth. That's not the case.
Holy crap, I never thought of that.
Well, and also, I don't know if you see that, let me share the screen again. Because I took this table off the site.
Yeah. Plus, the surface of the water should act like, what is that called again? All the cracks in the glass cause it?
The Luxembourg effect?
Yeah.
But even in this table here, it has a table of the refraction of light in air. Okay, and they have the conditions: the pressure, the wavelength. And so I highlighted these three different scenarios here. One at 300 nanometers, which would be a shorter wavelength, and 1700 nanometers would be the longest wavelength, and 633 would be, middle in between. And so the longer the wavelength, 1.000268, it's not bending as much as the shorter wavelength. The shortest wavelength is bending at 1.000286, so it's actually bending more. So the shorter wavelength bends more, not the longer wavelength. And so how can they get away with preaching that bullshit about saying that the longer wavelength bends more? It does not bend more. You can just look at the visible spectrum through a prism there. The red is the longer wavelength, and it is bending less.
Is that number a volumetric? Like, because you would think the index of refraction would change the more water it goes through. So how could they give like a set number without like a volume, like refraction per volume? Something. You know what I mean?
Well, they're all at the same conditions, the same temperature, the same humidity, the same pressure. So they're all compared under equal conditions. So, I mean, but they've gotten away with this for so long, That's why they can't really talk about it that much, because somebody can just out them. This is bullshit.
This is a globe earther, right? Not a flat earth argument, right?
Huh?
Who's presenting you this challenge? Is it a globe earther or a flat earther?
Neither. I was actually just looking into some research to talk about with Waptec here, and he thinks that the Earth is convex. Well, if it's convex.
Okay, so globe earther. It was a globe earther.
Yeah, globe earther, whatever. But
okay, because I was going to say that when I start seeing information that technical, right off the bat, I know, oh my God, it's not a flat earther, because they never go that deep. It seems like the people who do have some mathematical strength, intellectual strength, they're still kind of stuck on the globe. You'll never see a flat earth show you a chart or numbers, or some kind of ledger.
Yeah. So what I did was I turned that prism upside down, because it's easier for, I think, people to understand. If you're living on the inside, the concavity of the Earth, you have the red on the bottom here. The red is bending less than the violet. 750 nanometers versus 380 nanometers. So the shorter wavelength is going to bend up more away from the Earth as opposed to the longer wavelength. And especially when you get into the longer wavelengths like the microwaves and the radio waves. That's why you can see more with infrared waves, which are, they're longer than the reds here. You can see more with an infrared camera than you can with a normal light camera because it's a longer wavelength. So it's the same with radar. You can see your range in radar, in boat and marine radar, is greater when it's beaming out longer wavelengths.
Well, actually, you know what I just